Niklas is a PhD candidate at the University of Wisconsin-Madison, advised by Professor Josiah Hanna, who did a postdoc in our group previously. His research focuses on improving the data efficiency of reinforcement learning by controlling an agent's distribution of learning data through data augmentation and adaptive action selection. Currently, he's a research intern and consultant for Sandia National Laboratories, working on reinforcement learning for power grid management. And prior to his PhD, he studied physics and mathematics at the University of Pittsburgh, focusing on high-energy physics research with Professor Vladimir Savinov. I also mentioned that Niklas is coming to visit our group on Monday. So do invite anyone that is in Edinburgh to also drop by if you'd like to chat with him about his research and his interests. Today, Niklas, you're presenting a paper on how to do on-policy learning without using an on-policy sampling procedure. So I think that's a very interesting point. I really like the last sentence of your abstract when you saying that you on-policy learning requires on-policy data and not on-policy sampling. I think it's a very interesting idea. So yeah, I'm really looking forward to your talk, and please, looking forward to it. Thank you.
All right. Thank you very much for that introduction, and I hope you guys find it as interesting as Josiah and I do. So we're both pretty excited to share this work. We think it explores a pretty interesting idea in the on-policy versus off-policy reinforcement learning dichotomy. So the work I'm presenting is called On-Policy, Policy Gradient of Reinforcement Learning Without On-Policy Sampling. So as Samuel mentioned, this is so Josiah did a postdoc at Edinburgh before joining UW-Madison, and this work is actually largely inspired by a master's thesis that came out of Edinburgh, I think last year. So the paper that this is based off of is called Robust On-Policy Sampling for Policy Evaluation. The title might not be quite right, but we'll talk about that a little bit later. But anyways, before I actually get into the paper, I just wanted to give like a brief overview of what I do more generally. So the question that I'm really interested in is, this is a condensed version of like my thesis question, is like, okay, to what extent can we increase the data efficiency of reinforcement learning through data augmentation and adaptive action selection? So we'll start a little bit with just like data augmentation. So data augmentation, the general idea is that you're generating synthetic experience without actually interacting with the task by applying transformations to previously collected experience. So I have a couple pictures at the top of the slide here showing a bunch of different real-world scenarios that have different data augmentation functions just inherent to the task. So in the far left, we have some navigation tasks. These are actually robots that are in a warehouse that like Amazon uses. So what you could do, if you observe a trajectory of this little robot scooting around on the warehouse floor, you can translate and rotate that robot in any way that you would like, and you will generate additional data that agrees with the task's dynamics. If you look at the Cassie robot in the middle, you have this bipedal robot. So the robot is symmetric about its central sagittal axis. So I can actually swap the left and right leg movements to generate additional data. And then on this manipulation task on the right, some very basic physics knowledge would tell you that as long as the robotic arm and this cup are physically separated, the robot's movements should not affect the cup's movements. So in this case, if the robotic arm is sufficiently separated from the cup, I can translate the cup anywhere on the table. And then I will be able to generate additional data that matches the task's dynamics without interacting with the task. So there's been a lot of work on data augmentation, but there really hasn't a lot of work showing that data augmentation is really useful and it can really improve the data efficiency of RL. But there really isn't any work, exploring like how you should actually be applying data augmentation, why it works so well. So I mean, the two of the core questions that I've looked at thus far are like, how should I sample data from a given data augmentation function? And then how should I integrate this data into the RL training loop? So I have two works under review right now. One is currently at ICRA, or currently under review at ICRA, and the other one's currently under review at ICLEAR. So that's data augmentation, adaptive action selection. I'm not going to spend too much time on this because this is mostly what the current talk is going to be about. But the general idea is, how should an agent sample actions from its data collection policy to obtain low variance gradient estimates for policy improvement? Again, this is what we'll be talking about today, so I'll kind of gloss over this for now. And then there have been a number of other topics that I've been looking at recently and in the past. So my first paper was actually on action representation learning. I don't do very much in that right now. I do have peripheral interest in it though. And I am an intern at Sandia National Labs currently working on reinforcement learning for power grid management. So I have one paper is currently published. This is actually why I'm going to be going to Scotland. There's a conference happening on the 31st that I'll be attending. So we have one paper there, and then we have another one that's currently under review. And then something that very recently happened is I working with someone at Madison who wants to use reinforcement learning for adversarial machine learning. So we'll see where that goes. But so that's just a little bit about me, just to give you some insight into, like, where I'm coming from, what's my background. But let's go ahead and get started on the actual paper that we're going to be focusing on today. It's called On-Policy Policy Gradient Reinforcement Learning Without On-Policy Sampling, and this is authored by me and my advisor, Josiah. So we're going to start with just some overview about on-policy versus off-policy learning. So with on-policy learning, you have some policy pi that interacts with the environment a number of times and stores data in some buffer D. And then after you collect some amount of data, the policy updates using that data, and you get a new policy. And now you throw out the data that you just collected because that data is now off policy with respect to your current policy. So on policy learning, you update your policy using data strictly collected by your current policy. And this is in contrast to off policy learning. So what's typically happens with off policy learning is you just continually collect data and update your policy without actually throwing out your data. So you add it to what's usually called a replay buffer, and then you sample every time you want to update your policy, you sample data from your replay buffer. So basically, you're updating your policy using data collected by a superposition of all historic policies that you've used to previously collect data. So this is just a brief overview. We're going to be focusing on the on-policy learning side of this, but we just wanted to introduce this to bring to highlight a couple important terms that we'll be using throughout this talk. So on-policy sampling just refers to collecting data by sampling actions from the current policy. Both on-policy and off-policy learning typically do this. On-policy data refers to data whose state condition distribution of actions matches the expected distribution of the current policy. So this would be pi s. And then we're also going to introduce the third term, which we're going to talk a little bit about on the next slide. So if it's not super clear right now, just give it a moment. So we're going to introduce this notion of sampling error. So sampling error simply refers to a mismatch between our empirical state conditioned distribution of actions and the expected distribution under our current policy. So we're going to tease this definition out a little bit on the next slide. So we can easily talk about sampling error with a very simple example. So suppose we have a policy pi that puts equal probability on two discrete actions A and B at some particular state S. And let's say we visit S 10 times. So in expectation, after 10 visits to S, on policy sampling should yield A and B. We should sample A and B 5 times. But this is just an expectation. In reality, we might end up sampling B twice and then A 8 times. So this is an example of sampling error. So if we were to collect a bunch of data, let's say we collected 1,000 data points, our data set would likely be very close to what we would expect. But when we have small finite sample sizes, the empirical distribution of actions may disagree with the expected distribution of actions. But let's consider a different sampling strategy where instead of sampling actions from our current policy, let's just say we're going to first randomly sample an initial action, and then from thereafter, we're going to always choose the action that is most undersampled with respect to our current policy. So in this case, what will happen is we'll basically just alternate between A and B or B and A, and we're guaranteed to match the expected on-policy distribution. Now, the curious thing about this is that we're matching the on-policy distribution, but we're not actually using on-policy sampling. We're using off-policy sampling. So adaptive off-policy sampling can produce data that is actually more on-policy than on-policy sampling can produce. Now, why is this relevant to on-policy learning? So in particular, we're actually going to be focusing on on-policy policy gradient learning. So how is this relevant to that particular class of algorithms? So policy gradient algorithms perform stochastic gradient ascent on the parameters of a policy pi theta. So theta corresponds to the policy's parameters. And the idea is that these algorithms will increase the probability of actions that have a high expected return. So this is basically what reinforce does. And this is basically what all the other popular policy gradient algorithms do. So the equation at the top here is what people usually use to approximate the policy gradient. So it's essentially an average over data collected by the current policy. So you sample a bunch of data on policy, and then you compute this estimate in the brackets over here. So you consider the advantage and the log probability of the action. So if we have infinite data, if we sample from our policy, the empirical distribution of our data set should converge, or not should, it will converge to the expected on-policy distribution, which means that this particular Monte Carlo estimate of the policy gradient will converge to the true policy gradient. Now, we don't have infinite data. We always have to work with finite sample sizes when we're doing reinforcement learning because environment interaction is typically expensive. And even if it's inexpensive, it's just impractical to collect infinite data, of course. So we're always going to have to deal with some mismatch between our empirical distribution of data and the expected on-policy distribution. So the sampling error that arises from finite sampling causes noisy gradient estimates, and this might actually end up impeding learning. So intuitively, if you have a perfect estimate of your gradient, you're going to, the intuition is that you should converge to your policy faster, or to converge to an optimal policy faster. Also, it's something I forgot to mention at the very beginning of this. If you do have questions, feel free to interrupt. I can't see the chat, but just feel free to unmute yourself as we go along. Some of the ideas in here, as I've been talking about it with a bunch of other people at my university, some concepts are often spark a lot of questions. So if you have questions, just feel free to unmute yourself, and I'll be happy to answer them as they come up. So the core question that we're really so given all of this information, so off-policy sampling can produce data that is more on-policy than on-policy sampling. We're asking the question, well, do on-policy policy gradient algorithms learn more efficiently with on-policy data collected by any sampling method or with on-policy sampling? And our hypothesis is that adaptive off-policy sampling will improve data efficiency because on-policy learning requires on-policy data, not on-policy sampling. And to kind of talk about that a little bit more, the only thing that we need in order to get an accurate estimate of our gradient, the distribution of D just needs to agree with the expected distribution under our current policy. How that data is collected is irrelevant. It just needs to agree. So that's the basic premise of this work. So to talk about this a bit more, we're going to consider a very simple scenario. So we're going to look at the swimmer task. It's a common benchmark task used for a number of reinforcement learning works. So you basically train this snake-like agent to swim as quickly as possible, and we're going to consider doing this using an on-policy policy gradient algorithm. And for simplicity, we're just going to focus on 3 possible outcomes of training. So, or rather, we're going to assume that there are just 3 possible outcomes under our policy. So we have this random wiggling policy, which the agent just wiggles randomly and doesn't really make any progress. We also have this, and this will yield a return of 0. We also have this lunging policy where the swimmer curls up initially and then just slides forward and then makes no progress afterwards. So the agent makes some forward progress, so it gets a return of 50. And then we have this more effective swimming policy where the agent kind of repeatedly lunges itself forward and makes continual forward progress. Now, as a side note, this swimming behavior is a little bit odd because maybe you would intuitively expect the swimmer to be kind of like slithering like a snake. This is just the policy. This effective swimming policy that's shown on the right is just what on-policy policy gradient algorithms typically converge to, or this is like the best that on-policy policy gradient algorithms get for this particular task. Off-policy algorithms tend to perform much better on this task. So to further simplify this problem, we're also going to assume that there are 2 actions. 2 actions. So the first one is you prepare to move. So what this looks like is the agent bends outwards a little bit. So we can kind of see this a little bit if we look at this effective swimming policy. So the agent repeatedly bends outwards and then inwards to propel itself forward. So the outwards movement is preparing to move. And then the inward movement is attempting to move. So bending inwards after bending outwards should propel the agent forward. Now, if we run an on-policy policy gradient algorithm a bunch of times on this task, in particular, if we run PPO 100 times, what we'll see is that about half of the time, the agent will converge to a suboptimal lunging policy. So this is happening at roughly a return of 50. And then the other half of the training runs will converge to an effective swimming policy. So on the next slide, we're going to simplify the underlying MDP of this task to talk about how sampling error relates to agents converging to suboptimal policies here. So,
sorry to interrupt.
Yeah, sure.
Hi, Nicholas. Can we get back to the last slide?
Sure.
In the left down corner, you mentioned 2 actions. I'm wondering if this PPO agent is using the original action space, or we replace the action space to this simple 2 action.
So the original action space is the agent has, there are 2 links. I don't know if you can see my mouse, but there are 2 links on the swimmer. And the action space in the actual task is torques applied to those particular links. We're going to just, this is mostly for the sake of example, we're just going to condense the action space down to 2 discrete actions. So one is just going to be preparing to move and the other is going to be attempting to move. In actuality, the action space is continuous. So this is the next slide. We're just going to be, this is a simplification for the purpose of exposition.
Okay, thanks. So it's a discrete action space with 2 actions.
Right. Yeah. So that's the particular example that we're going to be focusing on here.
Okay, that's clear. Thanks.
Okay. So again, we have 3 outcomes: effective swimming, lunging, and random wiggling. And we have 2 possible actions: preparing to swim and attempting to swim. So here are 3. So here we're going to assume our agent repeatedly visits some state S, and then there's another state SL, and each leads to a particular outcome. So we have the returns here. Then we're going to go ahead and label our actions. So let's say our current policy places the following probabilities on each individual outcome. So with probability 0.5, we will sample a lunging policy. With probability 0.49, we sample a random wiggling policy. And with very small probability of 0.01, we will observe effective swimming. So after 100 visits to S, we may observe 50 random wiggling trajectories and 50 lunging trajectories. So, in expectation, we should observe 1 effective swimming trajectory, but in any specific realization of 100 samples, we might not. So in that case, what's going to happen is the agent's going to think that preparing to swim at state S will yield a return of 0, while while attempting to swim at state S will yield a return of 50. Now, the way policy grading algorithms work is the agent is going to increase the probability of actions that yield a high return. So if we don't observe this effective swimming trajectory, the agent will actually reduce the probability of preparing to swim at state S, and then increase the probability of attempting to swim at state S. So the effect that this has is it makes it even less likely for the agent to observe an effective swimming trajectory, and more likely for the agent to converge to a suboptimal lunging policy. It says slow swimming here. This is a typo. So let's consider. So so now let's consider a slightly different example here. So let me go back a little bit. So let's say we visit S 99 times, and we have 49 visits, 49 observations of random wiggling, and 50 observations of lunging. So what we could do to get a better estimate of the policy gradient is we can increase the probability of preparing to swim at state S and attempting to swim at this other state, SL. In that case, we are more likely to observe the effective swimming trajectory, and then our total sample size, then our total data set of 100 trajectories will match the expected on-policy distribution. So I want to pause here real quick to make sure we're on the same page and people understand this example. So if there are questions, feel free to unmute now and we'll talk about this example a bit. Otherwise, I'll go ahead and just continue.
Hello?
Hello.
Okay, hey, thanks. Yeah, I think the question makes sense. Sorry, the example makes sense. I'm probably asking this question a little early yet because I've read the paper and I see kind of where this goes. But I guess in this example here, you have two states which are discrete. And so if you sample lots of actions from here, you will see for any given state lots of examples of actions, and you can correct the empirical distribution towards like the expected distribution. But then when you have many more states, for example, in the multi-agent MuJoCo, was it multi-agent MuJoCo test that you have in the paper? Yep. Now suddenly it seems like, well, there are so many states here. In fact, I guess it's continuous. So I suppose infinite the amount of states that most states have 0 actions, and of the states that do have actions, you'll have at most 1. And so this doesn't really give you any information for a distribution. So what I was wondering conceptually is, I guess when you later try to correct for methods, somehow you're kind of correcting through the generalization of the neural network to states, which leads to kind of, yeah, it kind of confused me a little bit. I don't know if that. This
is a very good point to bring up here. So yeah, this example, we made it tabular for the sake of exposition. It's way easier to understand if we consider discrete states and actions. When you introduce function approximation into this, so like if you have continuous states, it's possible that trying to correct sampling error at some particular state might interfere with correcting sampling error at a different state. And then as you mentioned, sorry, I can't see your name, but as whoever spoke up mentioned, if you have a continuous state space, most states observe 0 actions, and then like an individual state has like, you will observe like a single action for it, like at most, just because the state space is continuous. So I think things will become a little bit clearer as we continue through the presentation, but I'll kind of give a bit of a forward reference on, how we kind of handle the continuous state space a bit. So The work that this builds off of is called robust on-policy sampling, and there are theoretical results in that work that show that, okay, if you have a tabular MDP, the method that they propose will correct sampling error. It's the same general idea that I'm talking about here, where if a particular action is undersampled, you should increase the probability of sampling it. So theoretically, in a tabular setting, this will help reduce sampling error and produce more accurate gradient estimates. So when you move to a function approximation setting, the method does deteriorate a little bit, though we have a couple little, I don't want to call them tricks, but the algorithm that we introduce takes some measures to make sure that we don't run into issues with function approximation. So that's probably not a super satisfying answer, but it's a very good question. Function approximation does kind of throw a monkey wrench into a lot of things, but empirically, once we get to the empirical results, we'll show that the algorithm that we're going to introduce, nevertheless, is able to improve the data efficiency of on-policy gradient learning. So if you have further questions on this later, once we kind of talk about some of the related work, feel free to bring this up again and we can have another discussion on this. If you have any follow-up questions, feel free to speak up now, or if I did an all right job answering.
Yeah, no, thanks. Thanks for the answer. Yeah, it would be pretty good. I really have to leave early, so but maybe we can chat some other time. I read the paper and I thought it was pretty interesting, but
thank you.
I did have some questions, so yeah, maybe we can chat some other time. I will send you an email. My name is Elliot, by the way, just in case, just so that you know when I send you an email. Okay, cool. Cheers. Bye.
All right. See ya. Okay, so pause for a moment if there are any other questions. Also, let me check the time real quick. I can't see my my clock. Okay, 9:30. Can you guys still see my screen?
So no, you stopped sharing when you.
Okay. Sorry. Let me share again. Sorry, the clock on my table is off. So
yeah. Oh, I can give you time if you need at some point in the future. Also, if you overrun, don't worry too much about it. It's
okay.
Yeah. If it's a bit often, I guess, overruns a little bit, then it's fine. So.
Okay. So let me go ahead and jump forward. Okay, yeah. So the idea is you want to increase the probability of actions that are undersampled with respect to your current policy in order to reduce sampling error in your entire data set that you will use to compute a policy gradient estimate. So now we're going to introduce the framework that we're going to use to reduce sampling error throughout RL training with an on-policy gradient algorithm. So we're going to have a behavior policy parameterized by some parameter vector phi. So this is the policy that's going to collect data. And then we're going to have a target policy that will update itself using an on-policy gradient algorithm. So the target policy is not actually going to interact with the environment at all. The behavior policy will collect all data, and then we're going to use that data to update both the behavior policy and the target policy. So this first part on the figure on the left over here, this is just showing us collecting data with our behavior policy and then updating the behavior policy. So the way that we're going to update the behavior policy, that will be the topic of all slides after this point. But the general idea is the behavior policy should update itself such that further data collection will bring our data set D closer to the expected on-policy distribution with respect to our target policy. And then afterwards, we will periodically update our target policy with the data collected by the behavior policy. So one of the added bonuses that we'll probably not spend too much time on here is that we can actually use additional data collection to make historic off-policy data appear on policy. which means that we can actually use D as like a replay buffer. So we don't actually have to discard data every time we update our policy. We can just use further data collection to adjust the data distribution to appear on policy. So we'll talk about that maybe a little bit more if there are questions. I have a couple backup slides on that, but for now I will leave it there. But this is the general overview of our method. We have a behavior policy that does all the data collection and tries to curate a data set that more closely matches the on-policy distribution of the target policy. So that way, when we update the target policy, we get more accurate gradient estimates and hopefully better convergence or faster convergence to a good policy. I'll skip that figure over here. So now, as I mentioned, all the slides after this, we're going to be focusing on, okay, how do we actually correct sampling error in our data? And the high level idea that I alluded to earlier is that we want to increase the probability of our behavior policy pi phi sampling actions that are currently undersampled with respect to our target policy pi theta. Now, the best way to do this is to compute the empirical policy. So just basically count the number of times, if you're in a tabular setting, count the number of times that each action appeared at each individual state and compare that against the expected probability density under our current policy. So if the probability of observing a particular action under our current policy is larger than what we actually observed, larger than what our empirical policy says, that means that particular action is undersampled at that state. So what we should do then is just increase the probability of sampling that action at that state. So while this method provides a very straightforward way to identify actions that are undersampled, so that way we can increase their probabilities, but it's largely impractical for RL training because we would have to compute the empirical policy every time we want to perform an update. And the empirical policy, you can compute it, say, using like a maximum likelihood estimate. So if you have enough compute to run repeated maximum likelihood fits all throughout RL training, then go ahead and do that. But this is really, really expensive to compute. So we're going to look for simpler methods. And actually, there is a simpler method. It's called the Robust On-Policy Sampling. This is the work that was the master's thesis from Edinburgh. So the paper is actually linked down here. It's called Robust On-Policy Sampling for Data Efficient Policy Evaluation in Reinforcement Learning. It appeared at NeurIPS. So the core idea of this work is that instead of trying to directly identify which actions are undersampled, they instead indirectly identify undersampled actions and then increase their probability. So the gradient that they use to update their behavior policy is just the negative log likelihood of the behavior policy under the target policy. Let me back up. I misspoke here. The gradient that they use to update the behavior policy is the log likelihood of the target policy under our current data set D. So we evaluate this gradient at the parameters of our behavior, of our target policy. So basically, we initialize our behavior policy equal to our target policy, and then we want to nudge the behavior policy in a direction that will increase the probability of actions that are undersampled. Now, the way we do that, the way they do that, here's the intuition. So the gradient of the log likelihood will specify a gradient direction that would increase the probability of actions that are oversampled relative to our target policy, which means that the negative gradient will decrease the probability of actions that are oversampled relative to our target policy. And that means, so by decreasing the probability of oversampled actions, you end up increasing the probability of actions that are undersampled. So instead of identifying which actions are undersampled, this method basically just decreases the probability of actions that the agent already observed. And what ends up happening is that this will increase the probability of actions that the agent hasn't observed. So I want to pause here. We can talk about this algorithm a little bit, or talk about this update a little bit if there are questions. because this is, I know that this was a point that needed to be discussed looking at the reviews for the initial submission of this paper.
Yeah, so is this, it almost looks like you're doing the opposite of imitation learning on the data you've already collected.
Right, so that's basically exactly what we're doing. When I say we, I don't mean, I wasn't on this this paper. It's exactly what they're doing. So yeah, so you essentially decrease the probability of actions that you already observed, and that will effectively increase the probability of actions that you haven't yet observed.
The question I have is that then, okay, hold on. So I guess it's like the trick is like that you are initializing the behavioral policy to the target policy in terms of the parameters. But still, like it's hard to parse that, like if you have like many actions, that this necessarily guarantees that like you will stay close to your target policy.
Right. So this is a very good question that we actually had to. So in the algorithm that we introduced, we'll talk about something that we do to make sure that we don't deviate too far. But yeah, one of the crucial points to point out here is that we always initialize pi phi, our behavior policy, equal to the target policy at every update, and then we just nudge it in a direction that will reduce sampling error. So we don't want to continually optimize. We don't want to perform a bunch of gradient updates with this gradient. In other words, we don't want to optimize the negative log likelihood at each update, and we want to make a local adjustment. And the way Ross makes sure that the update doesn't deviate too far from the current policy, they actually just perform a single gradient update every time they sample a new data point, and then they reset the behavior policy equal to the target policy. So the nudge that they're making to the behavior policy is very small in robust on-policy sampling. Does that answer your question here? I think it'll become a little bit clearer, hopefully, as we go through the next couple slides, but does that answer it so far?
The constant reinitialization then yeah, helps a bit to understand that. Thanks for that.
Okay, cool. So this is robust on-policy sampling. This is what our algorithm is basically going to be building off of. So the core results of this work is that, so the way they measure sampling error in this work as the KL divergence between the empirical policy pi d and the target policy. The empirical policy, they just approximate it as the maximum likelihood policy under the current data set. And the core result is that on-policy sampling will decrease sampling error at some state S at a rate of 1/m, whereas robust on-policy sampling, ROS, will decrease sampling error at a rate of 1/m². So it's much faster. So they have a bunch of empirical results on that you can check out in the main paper, but we're going to highlight some of the flaws on the following slide. So it worked really well for discrete action tasks, but not so much on continuous action tasks. So I actually jumped to the second bullet point here. I'll get back to the first one in a moment. So these are the figures below are figures from the original paper. So we see on-policy sampling, so it's sampling error on the vertical axis and then the number of data points collected on the horizontal axis. On-policy sampling is in orange, whereas robust on-policy sampling is the dashed brown line. Grid world is a tabular task. We see that ROS decreases sampling error faster than on-policy sampling. But when you go to a continuous task, that's what this continuous cart pull task is, there's really no difference between the two. It's actually struggling to reduce sampling error. So that's one of the drawbacks of ROS. It doesn't really work well for continuous actions. And also ROS focused on policy evaluation where the target policy is fixed. So in RL, we have to contend with a target policy that is continually changing throughout training. So that's a non-trivial thing to handle, and we'll talk about that a little bit. Could you tell me how much time I have left? I think I got, 13 minutes?
Yeah, but again, if you have to overrun a bit, it's not a huge deal.
Okay, so I'll gloss over some of this stuff a little bit. So one thing I do want to highlight. Actually, no, we'll go ahead. We'll come back to this if we have time. These are just illustrations of the drawbacks of ROS. But the two drawbacks, I'll just talk about them very briefly. One is that you have the potential for destructively large updates. So ROS is going to decrease the probability of actions that are currently sampled. But because the log increases as phi decreases, so the agent's actually incentivized to continually reduce the probability of really unlikely actions. So once an action becomes super unlikely, the updates are going to get very, very large, and that's not something that's going to make our behavior policies very unstable. And then I mentioned that ROS doesn't do a good job in continuous action settings. It's because it doesn't actually properly handle continuous actions. In particular, as this, a question came up earlier about how, like, there's nothing in ROS that makes sure that you are staying close to the target policy when you're trying to correct sampling error. So if you actually if you ran this gradient update a bunch of times, you would see that ROS would try to basically push the behavior policy all the way out to infinity, which is not going to correct sampling error ever. So I'm just kind of glossing over this for now. We can talk about it a little bit more if there are some further questions. And I'm also going to gloss a little bit over the actual method that we implement. Like the core takeaway that I want everyone to have of this work is that on-policy learning requires on-policy data, not on-policy sampling. And the way that you can get on-policy data without on-policy sampling is by just increasing the probability of actions that are undersampled with respect to your current policy. So we introduce a new loss. It's literally PPO, except we set the advantage equal to -1. And what effectively happens is that when an action is, this will reduce the probability of actions that we've observed by at most 1 minus epsilon. So this will, because we're truncating the loss at 1 minus epsilon, this loss prevents the agent from being disincentivizes the agent to, sorry, let me back up. It prevents the agent from being incentivized to continually push down the probability of unlikely actions. So this will avoid, the clipping avoids the destructively large updates. And we prevent the degenerate policies, so like I mentioned that ROS might produce a policy that just, a behavior policy that exists way out at infinity. We simply just try and keep the behavior policy close to the target policy, just using an auxiliary loss. We just reward the agent for minimizing the KL divergence between the target policy and the behavior policy. So we call our method Proximal Robust On-Policy Sampling because it's basically PPO with ROS. So this is also way faster than ROS and works really well in the RL setting when the target policy is changing. But I'm going to gloss over this a bit. We'll go ahead and jump to the empirical evaluation, and then we can come back if there are questions. So we're going to look at continuous action MuJoCo tasks. We do have some discrete action tasks in the paper, which aren't in the presentation. I can talk about those a little bit. But all I'm showing here is the continuous action tasks. So we have two baselines. First is PPO. The second is PPO with a replay buffer. Something I didn't mention is that we're basically using props on top of PPO, which is why we're using PPO and PPO with a replay buffer as baselines. So, using a replay buffer with PPO is not theoretically sound because you're updating the policy using data that is off policy. But it has worked in the past. I think that's actually what they did with the OpenAI did with their DOTA 2 work. They used PPO with a replay buffer. So while theoretically unfounded, it does work reasonably well. And we're going to include it as a baseline because it gives us an idea of what learning will look like with a replay buffer without trying to correct sampling error, and what learning with a replay buffer looks like with while trying to correct sampling error. So we're going to report the interquartile means that we achieve throughout training. And we're also going to take a look at the distribution of returns achieved after training. So this is just called the performance profile. We run 50 independent runs for all the curves that you're going to see, and all the shaded regions will correspond to 95% bootstrapped confidence intervals. So the first thing that we're going to do is we're just going to make sure that our method is actually doing what we would expect it to do. So we're going to compare it to Ross in the policy evaluation setting. So we're going to take a fixed target policy, and then we're just going to continually collect data with either Ross, props, or on-policy sampling, and we're going to see how sampling error decreases throughout the course of data collection. So we're going to collect 64 batches of data, and then afterwards, so our replay buffer is going to hold 64 batches of data, so we'll see sampling error decrease initially and then flatten out later. And we're using the same sampling error metric that was used by the Ross work. So this is what on-policy sampling looks like. Sampling error decreases as you collect more data, which makes sense. And then after the replay buffer fills up, it flattens out. With Ross doesn't really do anything in these continuous action tasks. This is unsurprising because even in a simple continuous cart pull task, Ross struggled to decrease sampling error. But props achieves lower sampling error than both Ross and on-policy sampling when using a fixed target policy. So props actually helps in the policy evaluation setting as well. Now, next thing we're going to jump to is RL training. So now we're going to show training curves for these 6 MuJoCo tasks. So the horizontal axis will be training time step. The vertical axis will be the interquartile mean return, which is just a more robust estimate of the average return. So this is what training with PPO looks like. And then PPO buffer. So this is PPO with a replay buffer that contains one historic batch of data. So in some tasks, it doesn't really do that much. So in Swimmer, we don't really see much of a difference. In Hopper, maybe we see a slight difference. In Walker, it actually helps a little bit. In Ant, it's detrimental. In Humanoid, it actually helps a little bit too. Half Cheetah, it's a little bit detrimental. When we use props instead, so props, we're going to keep around one historic batch of data. So it learns from the same amount of data as PPO buffer. The props curves almost always lie above the PPO and PPO buffer curves. So we're seeing that props is actually increasing data efficiency, despite the fact that it's actually using off-policy sampling. So across all tasks, we see better final performance. No, so in most tasks, or rather in some tasks, we do see better final performance, such as in Swimmer, Hopper, Half Cheetah, and Humanoid. Though props isn't necessarily guaranteed to get better performance. It's just it achieves higher return in fewer time steps. So it's not necessarily going to outperform PPO or PPO buffer in the long run. It just it converges faster. So we're showing that props is increasing data efficiency here. But next, we just want to see, is props actually reducing sampling error throughout training? So that's what, oh, sorry, I'm just getting ahead of myself. I can also show you the performance curves here, performance profiles rather. So the horizontal axis is return, and then the vertical axis is the fraction of training runs that have a return larger than the return on the x-axis. So the dashed line here at 0.5, wherever the curves intersect that dashed line, that corresponds to the median performance. And then the area under these curves will correspond to the average performance of the agent. So if one curve lies above another, that means you're getting better performance. So PPO, the performance curve looks a little bit like this. Here's PPO buffer. Sometimes it's above, sometimes it's below. The props curves always lie above the PPO buffer curves here. And it's actually, the median performance in Swimmer is actually quite large. So with PPO, the median performance is about 50. So about half of the runs are converging to that suboptimal policy that we talked about earlier. Whereas with props, most of them are converging to the effective swimming policy that we also talked about earlier. So again, this is just further showing that props increases the data efficiency of on-policy learning. And I'll skip over this, but we also see that props is decreasing sampling error throughout the course of RL training. we could talk about that a little bit more if there are questions. But the core takeaways is that, okay, we introduced this practical algorithm, this practical sampling algorithm that uses adaptive off-policy sampling to improve the data efficiency of on-policy policy gradient algorithms. And then we also, like, one of the core takeaways is that, like, we're showing that on-policy RL algorithms, policy gradient algorithms in particular, are more data efficient with props than on-policy sampling. And like the more general takeaway that we want people to, keep in mind is that on-policy learning requires on-policy data, not on-policy sampling. So some of the future work that we're currently looking at is like an advantage weighted props. So, if the advantage is 0, that particular state action pair doesn't actually contribute to the gradient at all. So you don't really gain anything by trying to correct sampling error for it. So by weighting the updates according to the magnitude of the advantage, we might be better able to, we might achieve more accurate gradient estimates that way. We're also looking at applications to large language models because these ones have large discrete action spaces. I know I talked about continuous action spaces here, but props also works really well with discrete action spaces. And we're going to talk with some of the people here who are much more familiar with LLMs and see if we can try props out on a fine-tuning task with LLMs. And some work that we have ongoing right now is using props in multi-agent settings. I could talk a little bit about that if there are questions, but I think I'll go ahead and leave it at that because I'm at time. And if there are questions about the application to the multi-agent setting, I know this lab does a lot of multi-agent work. So if there are questions, I'll be happy to answer them. But in any case, I mean, thank you for listening. I appreciate your attention. If there are further questions, I'll be happy to answer them. Or if you have to hop off, feel free to email me or check out my website. I think my email should be listed there as well. But thank you very much, and I'm happy to take questions right now.